FET, use that FET simulation one last time. I know some of you might be getting sick of this, but so you're looking for an announcement or an assignment that says tasks for U4L15. Task number 1, the do now. There's a link to the FET projectile motion. It's the same one we've been using for the last few lessons. And then right after that, there's U4L15 do now. It's a Google form. It's just 4 questions. Each question has instructions in it on what you need to do using the simulation, and then you just need to answer the questions. So you're just making some basic observations on what we've been learning about so far: altitude, range, drag, that kind of thing. So I'll give us about 9 minutes to work on this. I'll keep an eye on the responses, and I'll be here listening if something doesn't work, if you're not sure what to do. But you've got 9 minutes to work on the do now, and then we'll come back together to review. Go for it. All right, let's come back together and review this a little bit. I was checking out your responses as they came in, and looks like everyone's feeling good about content from the most recent part of chapter 5. Let's just go through and see what you figured out. So for the first question, anyone figure out why, even though we learned that 30 and 60 degrees add up to 90, and we did this in our previous lesson where you fired at 30 degrees, fires at 60 degrees, and they landed in the same place. So why aren't they landing in the same place this time?
They're not at 0, like the cannon height, isn't it?
Very good. And so this is actually something that, I don't know, maybe it says something about how tired I was when I was first doing this, but I read the chapter and I immediately opened the simulator and I started firing the cannon at these angles, and they weren't landing in the same place. And it literally took me probably about 4 or 5 minutes to figure out that, oh, my cannon isn't level with the ground. So that's one of the requirements, is that you have to be firing from the horizontal. And I think if you even look, I actually neglected to check, but they might even have the paths might even cross each other at that horizontal level. But then, yeah, they transition down. A lot of you got that. So what angle do you need to fire at to hit the little person standing near the target? It's funny, only a few of you actually got the full correct answer. Most people listed one angle. So what was one of the angles you could use?
75.
Yep, 75 was a common one, but there is also a second one. Good, -40. You can actually aim below the horizontal because the cannon is high up, and so you can have one shot below that. So those two numbers won't add up to 90 though still, because technically they are, again, your cannon is off the ground. So, all right, again, a lot of you sort of, some of these answers were creative as well, just to show you here for why they chose a statue of David to put down that. So I like that developer's name is David, don't know, decoration, the statue's famous. And so, yeah, one person looks like got it right. So can anyone share why the David in name?
I have an idea. I'm not sure if it's right though.
Yeah, let's hear it.
So like biblically, yeah, he was fighting some monster. It starts with like a G or something like that,
Mm-hmm.
and like he wasn't big enough or strong enough to like defeat it, so he had to use a slingshot to take it down. So
Yep.
that kind of has to do with.
Yes, he used a projectile. Mm-hmm. Does anyone know who David defeated in the Bible?
Goliath.
Yep, David and Goliath. Yeah, so Goliath was just kind of a big, monstrous person, and yeah, David defeated him by using a sling. Some people said that it could also be to put it to scale, but has anyone been to Florence? Has anyone seen the David? Is it life-sized?
It's 17 something not meter.
Yeah, it's huge. It's the height of several people. Yeah, it's absolutely enormous, which is kind of what makes it amazing, because it's still very much to scale in some ways. I mean, there's little studies they've shown that his hands and his feet are not quite proportional, but otherwise, considering that it was made by hand with no real computers or anything, it's pretty incredible what was done. But anyway, yes, but it's because of a projectile. So okay, and the last question then, this time firing in the drag simulation, you can see that even though drag was acting on the projectile in both situations, so you had drag acting at 60 and you had drag acting at 30, did it land in the same place? So that kind of tells you, I think it's interesting because I thought, well, if drag's acting on both projectiles, it should still land in the same place. It'll just be a little bit shorter than it would have been when there wasn't drag, but apparently not. Apparently the effect on altitude and range is varied enough with drag that you end up with two different landing locations. So those are some important takeaways, I think, from the previous chapter. Before we move on to new content, I wanted to give you an opportunity to ask any questions you have about the most recent homework. Were there any questions from, where was it? Here we go. Chapter 5, questions 21, 23, 24, and 25. Anything you left blank or wanted help on? All right, if we're feeling good, then you're all set. If you haven't submitted your answers to that, please do so. I know it's sort of repetitive to keep sharing your same digital notebook through Canvas, but it makes the grading really efficient for me. And so I'd appreciate if you could just, again, post a share link to your digital notebook through the assignment on Canvas. Okay, the next thing that I'd like to do is just give you a short lesson on the last part of chapter 5, 5.12, all about elliptical orbit and escape speed or escape velocity. Feel free to take notes on your digital notebook or on a piece of paper if you want. I have also posted a recording of myself going through these same slides that you can watch later if you want to as well. But we're going to cover what's called elliptical orbit, which you can see a picture of right here. It's just an orbit that has a slightly different shape. And in fact, this is probably the more common form of orbit that we see. I'll talk about what geosynchronous orbit is and escape velocity. And escape velocity is getting at this idea that we often hear that term, what goes up must come down. And that's actually not true if you're able to achieve what they call escape velocity. Hopefully you're not throwing a baby up at escape velocity, but if you did, that baby would just continue outward from Earth into space and would never come back. So I want to give a try and use some poll everywhere questions. You might have used these in other courses, but they worked well in my previous lessons. So the first question that I'm going to propose to you is a review question. And so you just need to open up a different tab on your computer and go to polev.com/hatesci2. And you should see this question that you can then answer, or you can use your cell phone, the text instructions. All the instructions are at the top of the screen. First question is, what are satellites? A, communication machines launched into space by humans to operate cell phones and TVs. B, moons and only moons around certain planets like Earth. C, any projectile moving fast enough to fall continuously around Earth. And D, man-made machines that take pictures of the surface of the Earth from high above. So go ahead and post your answer. And I'll show the results once we've got a good total number of responses. All right, we got 13 people here in class. I want to get to at least 10 responses. There we go. All right. So let's take a look, see how we're feeling. What are satellites? Good. Most of you got at the correct answer, which is indeed C. Any projectile moving fast enough to fall continuously around Earth. I put A though because when you hear that word satellite, I know that often what comes to mind is those little solar panel covered machines that we see floating around in space that we are mostly using for cell phones and TVs. But you have to understand that in the realm of physics, you can describe the moon as a satellite. You can describe Earth as a satellite around the sun. So it's sort of a catch-all phrase for anything that is in continuous orbit. Okay. So keep that definition in mind of what a satellite is. And now we've learned that the minimum amount of speed required in order to become a satellite, to actually rotate around the planet, is 8 kilometers per second, right? Because that matches the curvature of the Earth, right? If you're able to throw a projectile with that amount of velocity horizontally, it would never hit the ground because it would match Earth's curvature. Now, again, that is assuming that we are outside the atmosphere, right? That we're 150 kilometers up, and therefore drag from air and hitting things like mountains and trees isn't going to be a problem. So I think of that as sort of a circular orbit. However, that's not what you typically see because a lot of things that are orbiting our planet are going a little bit faster than 8 kilometers per second. And in that situation, if the horizontal velocity is a little higher than 8 kilometers per second, you achieve what's called an elliptical orbit, which is exactly what it sounds like. It is orbiting in what's called an ellipse, which is essentially sort of a wide, stretched out circle that has 2 foci. So mathematically speaking, you've got one focus here, one focus here. Now, in terms of gravitation, usually there's only one of these. One of the 2 foci would be the planet or the star, and it's just rotating around that. You can draw an ellipse pretty efficiently if you've got string and tacks. You can put a tack down on a piece of paper and another tack down parallel or like forming a straight line. Tie something like string or floss to it, and then get it taut with a pencil. And if you go circular in a pencil, you will draw an ellipse just like that. Now, things get interesting when you have elliptical orbits in terms of what's happening with the speed of the satellite as it moves around. And so I know you don't have much background knowledge of this, but I just want to see what you know. So one more poll everywhere question to give you. Question is, how does elliptical orbit affect the speed of the satellite as it travels? Option A, there's no effect. Speed of the satellite is consistent and does not change throughout the elliptical orbit. B, it goes faster as it approaches and passes the focus, which would be like the Earth or the sun, and slower as it moves away from the focus. C, it goes faster when relatively straight and slower when turning. Or D, the opposite, goes slower when relatively straight and faster when it's turning around. Take your best guess.
Where do we find this? Because I was looking and I couldn't see it.
What you should go is the instructions are on the top. You just have to open up a new tab on your computer and you can go to, do you see the address on the top, polev.com/hatesci2? I think if you type that address into like any kind of web browser, it will take you there. It should just pull up this question. Molly, did that work? All right, let's see how we are feeling. All right, we are torn between going faster as it approaches and passes the focus and slower as it moves away, or faster when relatively straight and slower when turning. So these are sort of the opposite, right? Because option B and option D are sort of similar to each other in that it's speeding up. But the correct answer is in fact B. It goes faster as it approaches and passes the focus and slower as it moves away, which is kind of the opposite of what C is. But again, I know you had no context for this. The way to think about it is you often hear this term in movies and things like that, when they're discussing, if you've seen Interstellar or any of these other things, they talk about slingshotting projectiles around something like a planet or a moon or a star. And that's what they're talking about, is that you're using the gravitation to speed up a satellite. And that's because if it can achieve an elliptical orbit, it does sort of get shot outwards after passing the focus. So here is the key takeaway from that question. Again, we're assuming we're 150 kilometers above or away from there's no air drag influencing here. If the satellite is in an elliptical orbit, it is going to move faster in this zone when it is closest to the source of gravity, right? The focus of what it's rotating around. It's sort of fired through at a really, really fast velocity here. But then as it moves away, it's going to slow down, right? So here it moves much more slowly as it sort of makes its way back. It's almost like it got thrown outwards, but then the gravitational force sort of slowly pulls it back in again. And so there's little animations you can find online that sort of show like a very fast rotation, then slows down, and then comes back in. And I'll talk about how they kind of use this slingshotting a little bit. So I like this example over here where you can see that this is occurring in multiple different ways. You have the moon rotating around the Earth. The moon actually has an elliptical orbit. It has what's called apogee when the moon is farthest away, and perigee when the moon is closest. Does anyone know what that alters on planet Earth in particular? Yeah, tides. If anyone's ever heard of spring tide and neap tide, the reason that high tides are different, sometimes high tides, the water comes really, really high up, and sometimes high tide really isn't that impressive, right? It's because of the positioning of the moon, right? The closer the moon is, its gravitational pull on our oceans is a little bit stronger. Earth also behaves the same way when rotating around the sun. We also have an elliptical orbit. Earth has what's called perihelion when we're closest to the sun, and I guess this is aphelion or aphelion. I'm not sure how that's pronounced when we're furthest away. And this is sort of counterintuitive. Does anyone know what season it tends to be in the northern hemisphere when we're in perihelion, when we're closest to the sun? What do you think? Would it be summer or winter?
Summer.
That's what I would think as well. That's what a lot of people think. But in reality, it's actually wintertime when we're closest to the sun. And I think it tends to be summer in the northern hemisphere when we're further away because, remember, the seasons actually have more to do with Earth's wobble and whether or not the northern or southern hemisphere is tilting towards the sun, not so much the distance between Earth and the sun. Anyway, kind of interesting. Don't know exactly some of the details behind that, but all right. So that's elliptical orbit stuff. Last question that I want to throw at you using Poll Everywhere is an open-ended question this time, just to get your thoughts on this. So now you should be able to type a response for this one. The question is, what is geosynchronous orbit? Think about that term, geo and synchronous. Even if you're not sure what it means, again, I'm not looking for a particularly right or wrong answer, but just see if you can figure it out. Type your answer and post it. All right, let's take a look. It moves with the Earth, so it spins as the Earth spins. A synchronized orbit of two or more objects. It's a good idea. Orbit around the Earth. It definitely does relate to that. Maybe like a perfect circle orbit around Earth and the same every time. Don't know. A season that syncs with the orbit of the Earth. I like the idea of a season. Same orbit path, an orbit that matches Earth's orbit. There you go. That's getting pretty close to it. It's an orbit with the Earth as the center. Or when satellites are orbiting at the same speed as a planet is rotating. There you go. Also a good one. An orbit that has the Earth in the middle, so as it moves relatively at the same time. All right, these look good. So I can see that you guys are really breaking down this word, right? That geo is referring to Earth, synchronous referring to the same time, or in sync, that kind of thing. So to get at the definition from that's given in the book, and a lot of you were hitting upon this, you first have to understand that satellites orbit Earth at different distances. And that makes a difference in terms of how much time it takes them to make a full rotation. So if you look at this image down here, the satellites that they call in polar orbit, do you see how they're pretty close to the surface of the Earth? There's not a whole lot of distance between the satellite and the surface of our planet. And so those satellites have to move really, really fast to make sure that they don't fall back down towards Earth. A lot of satellites at that distance, they're going to circumvent our planet every 90 minutes. Every hour and a half, they have gone completely around Earth, the planet, right? They're moving super, super fast. But if we can get a satellite further away, like this one here that's in what they call geostationary orbit, which I think is just another kind of similar term for geosynchronous, the further away they are, there is a little bit less gravitational force from the planet, and therefore they can stay in orbit while moving a little bit more slowly. In fact, if you can get to a distance of 5.5 Earth radii, which is the equivalent of 22,000 miles. So if we can get a satellite that is 22,000 miles away, so imagine that dotted line that was right here representing 22,000 miles, then that satellite is able to stay in orbit and rotate around our planet every 24 hours. And hopefully that number is familiar. Does anyone know how long does it take Earth to make a full rotation on its axis?
4 hours.
It matches, right? And so a satellite like that could stay stationary over a single point on the planet in perpetuity. And so a lot of you are getting at that in your definition, that these are satellites that are hovering over a single spot. Imagine having a satellite that is right above your head, 22,000 miles up, but it just stays there. Now, I think there is a little bit of adjustment here, and because Earth does wobble on its axis, and so I think those satellites do have to correct for that. So they are still able to move. But otherwise, we do make use of this often, especially with, again, TV satellites and cell phone towers and things like that, because they usually get the satellite hovering above a certain region, like certain parts of North America, that then they provide service to all the users in that area. So think of, again, geosynchronous orbit as satellites that can stay above one spot on the Earth permanently because they're matching the Earth's rotation, right? 24-hour orbit and 24-hour rotation of the Earth. Okay, that's geosynchronous orbit. Last part of chapter 5.12 is escape velocity. This is exactly what it sounds like. It is the speed, but again, I use the term velocity because it also takes direction into account. Needed to escape the gravity of a planet. So if you were to launch something off of Earth and you didn't want it to fall into orbit or to come back to the Earth, there's a certain speed you have to achieve, right? We have to overcome the energy that gravitational force is exerting on the object. And it turns out that on Earth, it's a minimum speed of 11 kilometers per second. That's the key number to know, right? If you can launch a projectile upwards away from the Earth, or I think even in a horizontal path, as long as it continues away from the Earth, at 11.2 kilometers per second, it will not fall into orbit around Earth. It will just continue to go and will never come back. However, what I didn't realize is that getting a satellite away from Earth isn't the only thing that you have to do, right? That's great. It'll move away from our planet Earth, but does anyone know what's still exerting a lot of gravitational force on every projectile in our solar system?
The sun.
The sun. And so if you wanted to really launch a satellite that then went somewhere else, like continued out of our solar system, you have to overcome the sun's gravity, which is much more powerful because that's what's holding Earth in place as well. And so it ends up, you've got to get to a speed of about 42. How do I go back here? Sorry, controls are going haywire. 42.5 kilometers per second. So pretty crazy. But then that would exit the solar system. And this is something that NASA actually has done. The Pioneer 10 was a satellite, it's pictured right here. It was launched in 1972. It took just short of, I think, a little more than 10 years to get to Mars. It passed Mars in 1984. And then they used, so they got it to the required 11.2 kilometers per second to get away from Earth. And then they used the gravity from other planets, kind of that slingshot thing that I was telling you about. They circled it around Mars and they circled it around Jupiter. And the gravitational force that was exerted on this by those much larger planets was able to sort of throw the satellite out into space. And it is now in interstellar space. As far as I know, they are not in communication with it anymore. It might just crash into something, or who knows, it might be discovered by another form of life. They have put like a whole sort of library of information about humans and planet Earth and everything on this in case it is discovered by anything intelligent, which the odds are slim, but who knows. Kind of interesting to think about. Now, again, this does relate to what we've been learning about with gravity. And so I wanted to touch on this. This is a table taken directly from your book that's looking at, it's listing the escape speeds required to get away from certain celestial bodies or astronomical bodies. So not surprising, the sun has one of the higher needed escape speeds. Right here, that's the highest, 620 if you were near the surface of the sun, because the sun is so massive, right? And we've learned that gravitational force is directly proportional to mass. The larger the mass, the more gravity it's exerting, and therefore it's going to be, you're going to need a lot of escape speed to get away from something like the sun. Luckily, we are a huge distance away from the sun, and therefore it's much lower at Earth's orbit. So here's Earth right here, the number we listed earlier, 11.2 kilometers per second. And not surprising, something like our moon, it's much lower because the moon is much smaller than our planet. And so it's sort of interesting to think about when we sent astronauts to the moon, it took a lot of energy and speed to get them off the Earth, right? 11.2 kilometers per second. But after landing on the moon, when they got back into the command module to leave the moon, it didn't take as much energy to launch from the moon, because the moon you only have to get to 2.4 kilometers per second to get off the surface of the moon and head back to Earth. Okay, so I know I threw a lot of numbers at you. This is just meant to be sort of a summary of the key numbers to take away. We're always talking about the horizontal, what's going to happen if you achieve certain horizontal speeds, right? So they've got this sort of what they called I think Newton's cannon, right? That if you could get a projectile fired horizontally from a height above the atmosphere, what are the speeds you would need to see some interesting things happen? And if you're able to get to that 8 kilometers per second, then you're going to get that circular, that's what's called orbit velocity. And they show that sort of perfect circle rotation right there. They don't list it here, but if you were to fire the cannon at a little bit more than 8 kilometers per second, you would get an elliptical orbit, which would look more like this, where it spins outward and then rotates back. And it would travel a lot faster when it was closer to the surface of the Earth and slower when it was further away. If you're able to fire a cannon at 11.2 kilometers per second, that's escape velocity. That would come off of the planet of the Earth, and this would never return, right? It wouldn't fall into orbit, it would just keep going. It might still fall in rotation around the sun, though, because you would need the 42.5 kilometers per second to get away and out of our solar system. So those are the key numbers to remember. Okay, any questions on that content from the last part of chapter 5? Okay, it's kind of cool. It relates a lot to space stuff, and that's going to be our next topic. Then we're going to move into a chapter kind of towards the end of the book and start talking about celestial bodies and how orbits work and things like that. So this is good knowledge to have. Okay. Then I wanted to use the last part of class to get you going on your Rube Goldberg project stuff, specifically making your simple machine. So if you head back to Canvas to our tasks list, this is task number 4. The first link right there, simple Rube Goldberg machine, is just a link to the project description. It's the same doc that I shared with you earlier. So if you want to just review the expectations and due dates and things like that, all that's there. None of that has changed yet, though again, we might make some updates eventually. And so the instruction is just review the instructions below. What I'd like you to do is put together a simple Rube Goldberg machine, film it, and post the video to Flipgrid. There is a Flipgrid assignment posted on our Science2F Flipgrid. Here's what it looks like. Again, I've posted a video of the simple machine that I made. This is the same video you watched in a previous lesson. but I would like you to basically imitate what I did. Put together a simple machine that contains at least 4 or 5 different objects interacting in different ways. The beginning of the video should be you explaining what's going to happen with the machine, right? Talk about what each part is and what it should do. Just basically show us what should happen. Then activate your machine. And it's okay if you need to sort of help it, if you need to push something, or, I don't expect it to work perfectly, but it should go to the end, right? You should be able to get your machine to achieve the final task, even if you do have to poke and prod a few things to move it along. So there's more detail just down here below, again, reminding you of some examples of materials you can use. The pictures I saw that you were posting all look great. Looks like most of you have at least some stuff you can use at home. My video is right here as well, but I'll give us the next 20 minutes or so, or like 15 minutes, I think. Let's come back, let's give it 20 minutes. So we'll come back here at 9:35. So I'll let you go right now to pull together your materials and see if you can put a machine together. I don't expect you to have a video done in the next 20 minutes, but I think this is just a good time to find a space to work in, test fire a few things, right? Try putting some stuff up and have it fall over. Just use this time to work on that, and then we'll come together, kind of reflect on it. I can offer advice or answer any questions you have, and then we'll be set. So let's come back to the Zoom room here at 9:35, and we'll check in again. So go for it. I'll see you then. All right, everybody, the time is 9:35. Let's come back into the room. Saw Nadia and Kenson got their videos posted, which is great. I didn't have time to watch them, but I will do so right after this, and encourage everyone to check them out as well. How to go for everybody else? Everyone feeling like they do have kind of a simple machine or a space they can set one up? All right. Yeah, some of the videos I've been seeing in my other classes look great as well. The advice I will give you, so this will just roll over into homework, but for your simple Rube Goldberg machine, the emphasis is on the word simple. Okay, don't try to go too crazy. Don't try to fire a projectile from across the room, right? As long as you've got 4 or 5 different items interacting in at least 3 different ways, I'd say, then you're in good shape. And again, it doesn't have to work perfectly. It just has to go to the end. The other thing that I learned when kind of playing around with this stuff, and I think you'll figure it out too, is that a lot of the stuff that you set up has to be sort of very close to collapsing anyway, right? It has to be on what I call like a hairpin trigger, right? That if you're going to have things fall over, they already have to be pretty wobbly, right? Because that's just going to make sure the machine works pretty efficiently. So, but again, this is meant to be fun. It's meant to try things out. So that's how you should approach it. Otherwise, the only other homework is just to read the very last section of Hewitt chapter 5, which I have posted down here. So read Hewitt chapter 5.12, and there's no reading check questions this time. Just take some notes for a open notes do now reading quiz that we'll have at the start of our next lesson. So that is it for me, kids. If you've got questions or need advice on machine stuff, I'll be hanging around here to chat. But otherwise, thank you very much. Have a good day and enjoy the weekend.
Thank you.